Yeah, thanks a lot, Manal. It's a pleasure to have you here. And you are from Alexandria University, Egypt, and we have a very nice collaboration. I personally and also QWorld. It's one of it's leading also the Q Egypt initiative within QWorld, and it's one of the very active places. So I'm very happy actually that you give the first talk. So please share your screen.
Okay.
I'm not. It doesn't work, the sharing of the screen?
I shared the screen.
I also cannot see it, unfortunately. Now. Perfect. Now we can see it. Thank you very much.
Okay. Thank you.
Thank you. And please, Manal, we are very interested in your talk.
Good morning, everyone. It's my pleasure to present my work today in QWorld. My name is Manal Khawasik. I am assistant lecturer in the Faculty of Science, Alexandria University in Egypt. Also, I'm a member in Alexandria Quantum Computing Group. I will talk about quantum qubit commitment protocol for communication systems. So let's go over what a qubit commitment scheme is. First, I will talk about the agenda, the main points. First, an introduction to bit commitment, then the proposed quantum bit commitment protocol, the protocol's structure, simulation, and finally the future work. Now let's go over what a bit commitment scheme is. Informally, it's just like a perfectly secured version of the commitment envelope. So the general commitment scheme will have two parties. Alice, who is the receiver, and Bob, Alice, who is the transmitter, and Bob, who is the receiver. Bit commitment has two main phases. The first phase is called the commitment phase, in which Alice thinks of a message, in general a bit. Alice puts her bit inside an envelope. The second phase is called the revealing phase, in which Bob is given access to the envelope. Bob can open the envelope and uncover the separate bits that Alice put. Commitment schemes have important applications in a number of cryptographic protocols, including secure coin flipping, zero knowledge proofs, and secure computation. But what if one of them is dishonest? So now let's go over the security conditions. Let's start with Bob. The security condition for Bob is called the binding condition, which means that once Alice has committed the bit, she can't change its value anymore. On the other hand, the security condition for Alice is called the concealing condition. That is, Alice wants the commitment to be hidden. This means that Bob is ignorant about her bit value before the revealing phase. So this is the commitment scheme. It satisfies two conditions, the binding condition and the concealing condition. Now let's go to the proposed quantum bit commitment protocol. The protocol proposes a commitment for any two classical bits at a time. The protocol started from Alice by preparing the commitment message as a 2-qubit state, following by a 2-qubit deportation from Alice to Bob. In the revealing phase, it's the time for Bob to open the commitment message. In parallel to the commitment step, Alice and Bob prove the binding condition by comparing the message resulting from the revealing step by the message resulting from the binding step. If the values are identical, then the commitment will be accepted, else it will be rejected. The proposed protocol operates under the assumption that the two parties might cheat. Also, the possible existence of an eavesdropper. The protocol's structure. The quantum 2-bit commitment protocol uses 7 quantum registers. The first, second, third, sixth quantum registers are under the control of Alpha, while the others are under the control of Bob. The commitment phase is represented by C, the revealing phase is represented by R, and this block is representing the binding phase. Hadamard gates are used in the proposed protocol in the preparation step in order to prepare an equal superposition on the first and second qubit. UF is a quantum operator that is used for selecting the states that Alice chooses to be hidden from the superposition. UF evaluates 2 for the target states and false otherwise. Then the partial diffusion operator is executed for hiding quantum states from the superposition. Partial diffusion operator has the following representation that is used as a tool for increasing the security of data transmission through channels. It performs the inversion about the mean on the subspace of the system that is entangled with the third qubit in state 0 and performs a phase shift of -1 on the other subspace of the system that is entangled with the third qubit in state 1. After that, Alice applies the unitary operator UA1, which is chosen randomly by Alice from the set of unitary groups to achieve the concealing condition of the protocol. At this moment, the 2-qubit state is ready to be teleported to Bob. In the proposed quantum 2-bit commitment protocol, the teleportation of 2-qubit states is a fundamental step during the commitment step. In the 2-qubit teleportation protocol, Alice has 3 qubits. 2 of them represent the 2-qubit states that Alice intends to teleport to Bob, while the third qubit is entangled with Bob in a non-maximally entangled GHZ state. A classical communication channel between 2 parties is also used. The combined 5-qubit subsystem state can be expressed by this equation, where this part represents the 2-qubit state that Alice intends to teleport, and this part represents the non-maximally entangled state. This equation can be expanded and rewritten like this, where gamma and delta are normalized complex numbers, while A and B are real numbers. The 2-qubit teleportation scheme in this proposed protocol uses the entanglement as a quantum channel and assumes that the information of the quantum channel is known by the sender but not the receiver. This teleportation can be performed using a probabilistic quantum teleportation that can be formulated as an ambiguous state discrimination problem and derives the exact optimal positive operator valued measure operators for maximizing the probability of unambiguous discrimination. The 4 measurement outcomes are 0, 0, 0, 1, 1, 0, and 1, 1. On the other hand, Bob needs only to make a unitary operation consist of specific Pauli matrices, and so the original state can be recovered. This T operation will be applied on the subsystem depending on the value of E. In the first case, if E equals 0, 0, then the original state is recovered without applying any Pauli matrices. In the second case, if E equals 0, 1, then the phase flip gate is applied on the fourth qubit. Case 3, if E equals 1, 0, then the bit flip gate is applied on the fourth and fifth qubit. Case 4, if E equals 1, 1, then the bit flip gate is applied on the fourth qubit and in the fourth and fifth qubit, and the phase flip gate is applied on the fourth qubit. So Bob is always getting the exact state of Alice. The teleported state can't be decoded, and hence the concealing condition is met until Alice sends to Bob the quantum operators UA1, G, and DAB1 over the classical channel, where Bob applies the conjugate UA1. Then Bob executes the Grover quantum operator once to perform the inversion about the mean, and so recover the states that are hidden by the partial diffusion operator DP. Finally, the decoding unitary operators DAB1 are prepared by Alice for each commitment value. And through the shared classical channel, Alice sends the corresponding decoding unitary operators to Bob to restore the commitment classical 2 bits that Alice has committed to Bob. This table illustrates the different decoding unitary operators depending on the value of the commitment message, where Alice prepares and sends the decoding operators to Bob, who applies them during the revealing phase. The binding phase is necessary in order to enable Bob to ensure that Alice will not cheat or change the committed message after commitment. Alice and Bob share one of the 4 Bell states. Alice prepares a secret unitary operator UA2 and applies it on the shared Bell state. Depending on the 2 classical bits that Alice chooses to commit to Bob, the second unitary operators are chosen. Bob chooses any combination of unitary operators and applies UB on the shared state. The binding condition is tested and executed by executing pre-agreed decoding quantum operators between Alice and Bob. The decoding operators are inspired from the superdense coding protocol and are applied on the shared state between the 2 parts. The resulting value from the binding phase is compared with the Bob measurement. If the 2 outcomes are equivalent, then this proves the binding condition, and consequently, the commitment message is accepted. Otherwise, the commitment message will be rejected. Now let's go to the simulation part. The proposed protocol has been proved mathematically in all phases and simulated using the Qiskit open source quantum development. The simulated circuit is composed of 7 quantum registers and 7 classical registers, and it combines all the phases of the proposed protocol. In the case of the commitment of the 2 classical bits 0, 0, Alice sends to Bob the DAB1 operators as X0, CX10, CX01, and H0, and she performs the identity gate on the shared Bell state. This histogram shows that the resulting value from the binding phase is equivalent with the Bob's measurement, which equals 0, 0. In the first case, if the commitment message is the 2 classical bits 0, 1, then Alice sends to Bob the DAB1 operators as X1, CX10, CX01, and H0, and applies the X gate on the shared Bell state. The resulting value from the binding phase is equivalent with the Bob measurement, which equals 0, 1. The third case, when the commitment message equal 1, 0, then this DAB1 will be executed, and also the Z gate. The histogram shows that the measurements of the classical registers are also equivalent and equal to 1, 0, which is the committed message. And this is the last commitment message, 1, 1, which equal 1, 1. And this is the gates that are applied. The histogram also shows that the equivalence shows that the measurements are equivalent in the fourth register, classical register, with 5 and 6 and 7 registers. Bit commitment is an essential summary and future work. Bit commitment is an essential primitive in quantum cryptography. It is the basic building block of many cryptographic protocols in which it provides security over distrustful parties. We proposed a secured quantum to bit commitment protocol for any 2 classical bits. The protocol contains 2 parties, a committer and a receiver, who share both quantum and classical communication channels. The main phase of this protocol are commitment and revealing phases, where the concealing and binding conditions are proved in order to accept the commitment message. The first equation represents the commitment step, and the second equation represents the revealing phase. The proposed framework utilizes different security layers to hide specific quantum states in a superposition using a partial diffusion quantum operator as an extra layer of security. The secured unitary transformations are applied by the 2 parties to meet the concealing and binding conditions and to verify the success of the proposed protocol. The measured outcome of the 2 parties are compared. The protocol operates under the assumption that the 2 parties might cheat and the possible existence of an eavesdropper. A 2-qubit deportation scheme is presented as an important step in the commitment phase, and a scheme of 2-qubit deportation is used using a GHZ phase. In the future world, the simulation can include a simulated noisy environment to check for the validity at different noise levels. And this is the proposed quantum to bit commitment protocol. By the end, I would like to thank all the authors of this work. Special thanks to my supervisor, Professor Dr. Ahmed Younes, and my thanks to Engineer Karim Safi for his support and help. Thank you very much, everyone, for listening. And now it's time for questions, if you.
Exactly. Thanks a lot, Manal, for keeping the time and for this very, very nice talk. It was very interesting. So at the moment, I don't see any questions on chat, and I think there was no questions on Discord either, but I have a question, and if somebody has a question, please ask. So I really like this protocol. And have you thought about including more parties, like yeah, more parties than 2?
I think the protocol can be enhanced, and it is a good idea to include more parties in the future work.
Exactly. Okay. Thanks a lot. So 2 parties, and would it make also sense to do like more than 2 parties, but make different type of commitment scenarios? Like do you also work on that? Like enhance it, sort of. Like using more qubits and so on.
Yes, I think the protocol can be more dynamic. We can use more parties in the future. This protocol just uses 2 parties, the committer and the receiver. maybe enhanced, maybe use more dynamic systems. I think these all ideas are very good to be considered in the future work.
Okay, thanks a lot. And then let me ask a final question, which is actually also now somebody posted that. I don't know what because it comes from an iPhone. So basically, what hardware one needs to implement it, or more generally, what are these experimental situations, or there you can imagine that one could implement it, or how feasible it is to implement it experimentally, and so on. Could you comment on these questions?
Can you repeat the question?
So the exact question in the chat was, what hardware does one need to implement this protocol? And my questions were similar, like how feasible is it to implement this protocol in an experiment? It's actually Oxana who is asking this, one of the invited speakers. I mean, Karim is writing that photonics might be...
I can...
Yes?
I can't understand the question well. Again, I don't know what is the...
Hardware?
I can't understand the question. I can't understand.
Okay. The question was like whether one can implement it in physically, but actually Karim answered is that probably one can implement it with photonics. That's one way of doing it. In quantum communication scenarios are usually implemented, and quantum communication and security scenarios, photonics is great, I guess. And then Muhammad Daoud also asked a question: did you consider errors in this protocol? This also goes to the experimental realization and how much error, how big the error stability is. And in what way would you suggest to mitigate these errors?
We make a simulation for the protocol, but in a real environment, we didn't execute a real the protocol in a real environment. So it is, as I mentioned, in the future work, we will try to execute in a noise environment and a real hardware, maybe.
Okay, so real hardware. So you are thinking about implementing this on real hardware, some type of...
Yes.
That was the first question.
Yes.
Okay. Thanks a lot. And also you want to implement some error mitigation type of techniques, right? Thank you very much.
Thanks.
Okay. Thanks a lot for this great talk, Manal. It was very nice, and hope to see you at the next year as well here. And now we are going to the invited...
Professor, sorry for interruption. Like after each talk, we should stop and then start again.
Exactly.
Yeah.